Hello, good afternoon. For next 40 minutes or so, we are going to share our journey regarding database migration from legacy database to YugabyteDB. What are the steps involved? How did we perform the database migration strategy? Um, uh, what all we covered in our POC, and what are the challenges that we have faced? How did we overcome those challenges? All of this we are going to cover in the presentation. So a little bit of introduction about ourselves. I am Anjani. I have a Coxin with me. Coxin will start his introduction first.
Hello everyone, my name is Coxin. So I'm currently a senior software engineer in Singtel. Previously I was working with enterprise identity platform, and I'm currently a core contributor in data as a service platform, and my main focus is to migrate existing application into Yugabyte platform.
Hi, my name is Anjani Jha. I'm a senior software engineer in Singtel. I've worked with identity platform as a backend developer and currently working in the data platform team, same as Coxin, mainly focused on migrating existing applications to the YugabyteDB. So let's begin with the proof of concept we have conducted to comprehend the advantages and disadvantages of YugabyteDB. The initial phase of this project involves a comparative study between the YugabyteDB and other distributed database systems like CockroachDB and distributed Postgres. Coming to the comparative study, uh, uh, before migrating our current systems, we conducted this study among different distributed database providers. The key aspects for us were high availability, consistency, scalability, where we can see YugabyteDB fits perfectly in comparison as it provides high availability with automatic failover and replication. It provides strong consistency in single cluster and is designed for horizontal scaling. So even if DB Engine's ranking is higher for distributed Postgres and CockroachDB compared to Yugabyte, we find a similar performance among all three and some more benefits from the Yugabyte DB, like other non-technical aspects. Like day-to-day support, local on-site support from Yugabyte team during our deployment phases, support from the team on day-to-day basis was a huge help for us. So some key benefits of YugabyteDB, be it high performance, fault tolerance, strong consistency, which makes it more fit to our application's needs. And yeah.
Coming to this part, I would like to share on our POC journey, and let's start with management console. So as we know, Yugabyte offers multiple ways to install and set up the console. As part of the POC, we want to explore each and every single options. We try it out and we try to identify the one that fits Singtel the most. At Singtel, we try to automate as much as possible, and that becomes one of the most important criteria when we decide on which one we are trying to go with. Aside of that, we also consider the ease of monitoring and also ease of scaling. So we first started with EC2 console. What we found is that it's harder to automate the deployment, and it's also harder to monitor the console's health. Similarly applies to replicator console. We find that we are unable to automate the deployment as it's manual. It's done manually through the replicator UI. And since that our setup requires to go through a proxy, we cannot share a single proxy between the console and replicator UI. So finally, we decided to go with Kubernetes console as it fits all of our requirements. Next, I would like to share on our POC journey on selecting the cluster. So we went on to try out each and every single cluster setup. We try on EC2, Kubernetes, and also on-premise. We find that there isn't any much difference between the cluster options except for connection latency. Since that our application are deployed in cloud, we noticed that there is a minimum latency when we connect to on-prem cluster. So, and also as part of the company policy, we are only allowed to store confidential data in on-prem. So right now, we are going with on-premise cluster. And in the future, we also plan to have an EC2 cluster to cater for all the other application that doesn't store any confidential data.
Okay. So we come to the data migration strategies now, and what kind of challenges we have faced, how we overcame those, and also we cover why do we need a database migration strategy, what have we accomplished from it. Yeah. So first we try to understand our application which we are trying to migrate. So it's one of the critical services internal to Singtel, and its responsibilities are mainly authentication, authorization, and KYC, as well as other services. So identity platform is one of the identity providers, and it makes Singtel platform work with the ID and verification. Apart from the authentication authorization, it also provides other services like user registrations.
So we have set a few success criteria for this project. One of it is that we want to seamlessly integrate our existing application into Yugabyte. And that means we want to have minimal to no business disruption. And the change between the database should be transparent to the end user. Secondly, we want to move all the data out from legacy data source into YugabyteDB with no data loss and also with guaranteed consistency. And finally, we want to establish a standard procedure to onboard future application smoothly. So coming to this part, I would like to share a little bit about how we set up our management console in production. As you can see in the diagram, we not only have Yugabyte management console deployed, we also have several other components deployed. So as I mentioned just now, we focus a lot on automation. We try to automate all the components deployment by creating pipelines, and we are applying pipeline as a code practices in Singtel. And this allows us to have a better version control and maintainability. For data storage, we are utilizing EFS as persistent volume, as this allows us to support multi-zone deployment of the console. So on top of the safety of EFS, we want to have a secondary backup of the console data itself. This is why we deployed a cron job that takes backup every night and upload it into S3. And there will be another ad hoc job that takes the latest backup from S3 and restore it to the console. For user authentication, we are utilizing OIDC in Azure. And we also have internal password manager for super user access, where we have a standard procedure to request for the password access. And for observability, we deploy a metric bit that will forward all the metrics from the Prometheus container in the console to our own Elasticsearch. And this allows us to integrate with our internal support system and also set up alerts. And finally, as you can see, we also deploy our custom Prometheus and Grafana. This allows us to create our own alerts and also our custom monitoring. We also, on top of that, we also have a slow query component deployed. And this turns, on top of that, we also have a slow query component deployed. This converts the slow query response that we got from the console API and turns it into a Prometheus compatible metrics. And this allows us to configure alerts, and we get to know about slow query incident in production as soon as possible. Coming to this part, I would like to share on how we set up our production cluster. As you can see from the diagram, we have 2 data center prepared, and we created 1 cluster in each data center. So our primary cluster serves as an active cluster, which our client will connect to it. And then our secondary cluster serves as a failover cluster, which in the event there's a disaster, our client just have to connect to the failover cluster and resume their business. So each of the cluster consists of 3 nodes. And if you notice that each of the data node are physically isolated in different racks. And the benefits of doing this is that it reduces the chances of all nodes going down and bringing the cluster down. And at any given time, we only schedule incremental backup from our primary cluster into the NFS. And we also configure a sync cluster replication from the primary to secondary cluster, and we also enable point-in-time recovery in the primary cluster. Coming to this part, I would like to share on how we automate our database node setup. So as we already know, Yugabyte is a distributed database, and scaling plays an important part in it. But to scale and cluster, we first have to provision node and set up the environment, prepare for it. And there are multiple ways of doing it. One of the easiest ways is that we log into a node and do it manually. But this will cost the developers a lot of time. And at the same time, there could be a lot of inconsistency between each of the data node. So one of the way to resolve this is to apply infrastructure as a code, in which Singtel, we are using Puppet for it. So I'd like to walk you through on how the development process will be. So at first, if there's any changes, the developers will push the code changes to the code repository. And after the review process is done, we won't merge in the master, and Puppet Master will hold the changes every 15 minutes. And if there's any changes, it pushes to all the data nodes that has Puppet agent installed. And Puppet agent will make sure that the state of each node match the desired state that is set by the Puppet master. So the benefits of doing this is that we have ensured consistency, as all nodes are guaranteed with standardized configs. And we have also improved security because there are less human intervention and reduce human error. And since that all the codes are committed to a code repository, all of the changes are tracked. We have a better version control and also transparency. And last but not least, by going to this approach, we heavily reduce the development time cost. Coming to these slides, I would like to share on how we enhance on the observability of the console and also the database. So Yugabyte Console provides a great observability out of the box, such as alerts support, Grafana and Prometheus metrics, and also expose a lot of useful API. But on top of that, we want more control towards observability. And how we did that is that we first pipe all of the metrics and logs into our Elasticsearch. So this allows us to configure our own alert threshold and also integrates with our internal support system. So on top of that, we deployed our custom Prometheus and Grafana for custom monitoring and alerts, and also a slow query, which will turns slow query response from the console into a Prometheus compatible metrics. And this allows us to set up alerts for slow query. Moving to the next part, I would like to share on how we replace our legacy LDAP with YugabyteDB. So the current problem that we are facing in Singtel is that we have multiple legacy LDAP with not. Coming to this part, I would like to share on how we replace our legacy LDAP with YugabyteDB. So in Singtel, we face multiple issues with our legacy LDAP as we are running out of support of it, and we find that LDAP is harder to scale, and it's a risk if we continue to maintain it. So in the end, we decided to migrate out all the data from the legacy LDAP into YugabyteDB and use it as a credential store. So how we did it is that we wrote a cron job that performs a one-time migration from all the LDAPs into YugabyteDB. And then we wrote a replacement service that replaced all the LDAP functionality, and it will route the traffic primarily to YugabyteDB and fall back to LDAP in case there's any exception. The benefit of doing this is that it prevents any disruption to business in the event that there's any Yugabyte outage. And also this replacement service will keep both the data sources in sync. The benefits of doing this is that we have a better maintainability and flexibility, as not everyone understands LDAP protocol. And furthermore, we also have a better scalability and performance as we can scale as our business grows based on our business requirements. And we also have better observability with the help of Prometheus and Grafana.
Okay, so we have covered the LDAP migration. Apart from migrating LDAP and using Yugabyte as a credentials store, we are also performing a database migration here from our legacy database, as we discussed earlier. Our end goal over here is during incremental cutover phases, services can migrate gracefully without any failover. So we have multiple services connected to our legacy database. The router service is a middle layer. So the strategy is to have the router service in. Apart from migrating LDAP and using Yugabyte as a credentials store, we are also performing a migration for legacy database, as we discussed earlier. Our end goal over here is during incremental cutover phases, services can migrate gracefully without any failover. So we have multiple services connected to legacy databases, making it so crucial for our strategy to provide data consistency for all the services. That's where we have come up with a service called as router service here. Why do we need the router service? How it is related to our database migration? Let's look into this. It helps the services to seamlessly migrate to Yugabyte as the write operations are happening on both legacy database and YugabyteDB. So any update operations has to go first to the legacy database and YugabyteDB as a secondary. Router services treats the legacy database as the primary and the Yugabyte as a secondary data source. That in the initial setup and the initial migration, any failures happening in our new database setup doesn't give any service failure, doesn't give rise to any service failure. A router services still continues writing to the legacy even if Yugabyte failure happening. If there are any write failure happening on the legacy, then we gives a failure message to services. This is until the full cutover is completed and all our new all our services are connected to the new YugabyteDB, which is up and running and without any failure for some interval of time, which is our full cutover timeline. Over here, for read operations, router has a configuration for how much read we want to direct to YB and how much we want to serve from the legacy database. If any failure happening on the Yugabyte, all the read operations are directed to the legacy and vice versa. Services don't get impacted of any issues while migration is undergo. So here we can see that the X is the configuration percentage for which it can set to 0 if there is any failure happening on the Yugabyte. And at the time of full cutover, it can be set to 100%. YugabyteDB Voyager, uh, why does it come into picture in our data migration strategy? So For the database migration, we are using a tool called as Voyager, provided by Yugabyte. This is to manage end-to-end database migration, including the cluster preparation, schema migration, and data migration. Voyager safely migrates data from Postgres, MySQL, Oracle databases to YugabyteDB managed and the core open source database YugabyteDB. Here we can see that all of these databases are supported by Voyager, and we will further see how are we using it. So we have created a job here for providing a smooth and configured Voyager migration to provide a control to the applications team for using a Voyager migration pipeline. So Voyager migration pipeline has some simple steps like prepare data source, export and import schema, export and import data. While analyzing the exported schema for any modifications are required, we can perform that either offline or we can perform that via some scripts from this job. So here we can see that the prepare data source is one of the crucial step where we prepare our source database. The second one, the export schema and export data comes into picture. Before that, we analyze it, and the import schema and import data comes in the end. So here we can see that the Voyager configuration, how we have configured it. The username and passwords, of course, are in the secrets. The schema migration and data migration are the two major steps. The schema migration, if there is any issue happening, if there are any failure scenarios, we can still continue with the post data as true, which actually enable the refresh and views flag. Exclude objects list. If we want to exclude some of the like some triggers we want to exclude, or probably we do not want to include the views, we can write here the view or the triggers, and that will be excluded. Here in the data migration, we can see that the parallel jobs and batch size are also configured, which are also using the Voyager flags. Tables list are the configuration where we add the tables of data which we want to migrate from our source databases. Here we can see that there is another section called as SQL migration configuration. Here we have the database schema which we want to migrate. We want to create the users roles, or we want to change the schema name. All of this we can perform using the SQL migration configuration. If we want to add a new tables or create some tables or update some data on top of the migration already happened, we can use this particular scripts, SQL migration configuration, to run those SQL files. Apart from the Voyager configuration, we had to use something called as Yugabyte client, which uses here this job uses the YSQL.sh to perform this user role creations. So here users and roles creations are managed by this job. And running this script, which provides automation and removes the manual script running in production while setting up our YB database. Once the Yugabyte client has completed its pipeline, we run the Voyager migration pipeline, where we have earlier seen that the prepares data source, import schema, analyze or modify the schema files generated. Again, we can do the import schema again, because the analysis or modifications, if we have completed, we need to de-import it using a different set of flags, and then the import data with tables list. Okay. So as we know that our application has two databases running simultaneously. Right? So even if we have completed our database migration with the Voyager and Yugabyte client, our databases, there are two databases which are running simultaneously, and there are some services which are connected to legacy database itself. right? Which gives rise to this data inconsistency issue between our target data source, which is YugabyteDB, and the source, which is legacy databases. To resolve this issue, we have a cron job running with the sync up frequency as uh, okay. Uh, so we have completed the database migration strategy, the LDAP migration we have completed, how we did the cluster setup. Now we come back to the console UI. There is a Yugabyte Anywhere console UI provided by Yugabyte. But here in Singtel, our process are to have some due diligence. All the changes have to be auditable and authorized. Yugabyte Anywhere is a console UI where an admin user has the permission to perform some critical operations like create a new universe, delete the universe. For any admin user to perform such operations, we have integrated this UI in our Singtel wide internal systems, provided for users, roles, authentication, and authorization. For any third-party UI to be onboarded internal to Singtel, we provide this, and this is mandatory. It gives us benefits like auditing the changes, password management, as well as roles management for any developers or production support systems to get easily onboarded onto the Yugabyte console.
So after we're done with Yugabyte onboarding, we wanted to find out Yugabyte's maximum capabilities and how well it performs under extreme condition. So in order to achieve that, what we did is we wrote a custom benchmark tool to simulate all these cases that we want. So um, so starting with defining a table schema, as you can see in the top left section, we have a table with 10 columns and one index key and also a non-index key. And then in the top right section, you can see our cluster specification. We have Rail 8.9 installed, and we have 24 CPU in total, 144 gigs of RAM in total, and 450 gigs of disk space in total. So as you can see in the bottom part, this is a sample row in our database. So each of the column has a max out 255 length. So keep in mind that all these data are sent across from the cloud to on-prem cluster. So starting with the first test case, we're going with all reads on a single table. So starting with the first test case, we are trying out all reads on a single table. So we run this test scenario for 60 minutes, and we have 1.5 million records in the table. There's a sample read statement on the left-hand side. As you can see, we are selecting a row from the table based on the index column. So to our surprise, we achieved almost the 4,000 TPS and around 50 millisecond per operation, which is very impressive. So next, instead of doing a single table read, we are trying to read from 20 tables at once. So our test scenario comes with 20 tables, 10 columns each table, and 1.5 million records each table, totaling up to 30 million records. And in every single read, we are joining all 20 tables at once. So to our surprise, we achieved 1.3K. So, coming to this slide, instead of doing a single table, we are testing on 20 tables. So our test scenario comes as 20 tables, 10 columns each table, 1.5 million records each table, totaling up to 30 million records. And in every single read statement, we are joining up all 20 tables on an index column. And to our surprise, we managed to achieve 1.3K TPS at around 374 milliseconds of latency. So we are done with all reads. Now we are trying out all writes instead. As you can see on the left-hand side, this is our sample write statement. So at first we begin a transaction, and then we insert into 20 tables, and then we commit it at once. You might also notice that we only ran this test scenario for 15 minutes. That's because we already ran out of our disk space at the end of 15 minutes of the test. So we managed to achieve 13.5 thousand TPS at around 926 milliseconds, which is very impressive and it surpassed our expectation. So coming to the last part, instead of doing all reads and all writes, now we're going to combine both of them. We are doing random reads and writes on 20 tables, and we managed to achieve 4,000 TPS and 266 milliseconds of latency, which we are very
Okay.
Coming to the next part, instead of doing all writes and all reads, we combine both of the test cases together. So our test scenario goes as 20 table, 10 column each table, and we perform random reads and writes. And to our surprise, we managed to achieve 4,000 TPS combined with reads and writes, and also 266 milliseconds per operation. On top of that, we also want to study on how well YugabyteDB performs under aggregation. So for our read statement, we are selecting max on a column in every read. So we ran this test scenario for 60 minutes on a table with 1.5 million records, and we managed to achieve 25 TPS, which is still impressive. So here's a summary of all the test case that we have ran. And do keep in mind that all of these scenarios are extreme and they are unrealistic and unlikely and shouldn't be in production. And all of these results are collected with no errors. As you can see, we also ran some test cases where we select on non-index columns, and we still managed to achieve 24 TPS on single table, which is very impressive. So coming to this part, here's our summarize. So coming to this part, here's the summary of our stress test results. Do keep in mind that all these results are collected without errors, and all these test cases are unrealistic cases, and they are unlikely and shouldn't be in production. And you might also notice that we ran some scenario where we query based on non-index column, and for example, single table or reads, and we still managed to achieve 24 TPS, which is very impressive. So on a final note, I would like to talk about the challenges and the experience with onboarding YugabyteDB. So first, during the onboarding of Management Console, we noticed there's some gaps in cluster backup, and we did assist a YugabyteDB team to work on the backup improvements and release a new version of it. And later on metrics monitoring, we noticed that the Prometheus metrics collected from the data node is not universe-based, and we have to do manual aggregation on it. And then later on, we try out with the console metrics, which turns out it's missing some metrics which we cannot rely solely on it. And finally, we also notice some mismatched data type when we migrate the table schema using Voyager. And also, there are certain functions that appears in the source database, but it's missing in the target database, where we have to create some custom function to cater for that case. And finally, to share on the experience to onboard with YugabyteDB, first of all, we notice the biggest advantages is that it heavily reduced the development time cost, especially in cluster provisioning, which shorten the overall time cost into just minutes. And also, we like that YugabyteDB it's providing ease of adoption because it's compatible with Postgres and Cassandra, which most of the developers already familiar with. And Yugabyte also provides comprehensive API for custom integration, and they also have extensive support for Prometheus and Grafana. And finally, YugabyteDB offers great performance and scalability with the help of high availability, which ensures the least possible business disruption, and also flexibility in scaling the clusters, which allows us to fully optimize the resource usage.
So in conclusion, we have covered the YugabyteDB, why YugabyteDB, the POC journey, the database migration strategy, how did we do the setup, in the stress test, what did we find out, and the comparative study between the Yugabyte and all other databases. We have onboarded onto the YugabyteDB, and we have found out some great benefits for it. Thank you.
Thank you.